Hi, this is Rick Jones. A few customers of mine told me that my software was confusing and impossible to run. So I borrowed the neighbor's 12-year-old son to run the software while we model a 622 cubic inch drag engine that Darin Morgan modeled on Pipemax in a recent members only dragboss video. Darin Morgan gave me all the information which I wrote down for the youngster. The young man's name is Billy. I walked him through the software, which took about an hour. And what he's doing right now is just entering all the data on the main form. And that's all you have to do to design the cam. All right, well, we just entered 15 for the mechanical compression ratio. We're on to the valve diameters. Right below that, the valve stem diameters. Now here's one coming up, TD divided by VD percentage. That's the throat diameter divided by the valve diameter. And below it, throat area is calculated from that. Now he's entering the intake port, minimum cross-sectional area, now the average cross-sectional area. 28 inches of flow bench test pressure, 480 CFM at the conversion slip to 619, 302 on the exhaust, 1 inch max port CFM lift, and 525 on the intake, 358 on the exhaust. Now he's going to 7,800 for max horsepower RPM. Everything else is pretty much set here. It's naturally aspirated, and we got to put the right fuel in. Now the rocker arm ratio is 1.9 on the intake, 1.8 on the exhaust. It's not a hydraulic, so you turn that off. Put in 24 thousandths lash for each, and 30 thousandths valve train deflection on both. All the buttons below that you see are all set in automatic mode. You don't have to do anything. So the cam's a 288, 310, 1.045 thousandths lift on the intake and 1.025 on the exhaust. Here's Pipemax's suggestions. 288, 316 duration on 117. You can put a 981, a 1057, a 163, or 1.218 on the intake. 1248 to 1350 horsepower. Is anyone confused yet? Well, let's show you how we do a max effort. There's a potential button, there's a potential VE. We'll push the button and bam, 291, 1.206 lift, 182 on the exhaust. Did that confuse you? Okay, I think we're good as far as the confusion goes on this form. Let's go ahead and generate that cam on the generation form. You select the cam journal desired, click the calc base circle button, and make sure you put in the roller lifter wheel diameter. You can also select asymmetrical intake, but I wouldn't do that for this one. There's a smooth button, and you hit Analyze Profile. No message box has popped up, so you generate the profiles. There's the intake saved and the exhaust saved. And here's the names of them. It has 332 is the duration, 563 is the lift, 1378, that's rod to stroke, radius of the roller lifter, radius of the base circle, ramp height, and 30 thousandths deflection, and it's an intake. So the name actually describes pretty much everything you need to know about the profile. And we can draw a pretty picture for you too. Now we're going to run over to the valve to piston form real quickly. And it already loads the camshaft profile that we saved. It's still in memory. All you have to do is put in the valve angles, but we already have those. Calculate the 1/910 exhaust. That looks to be good. All depends on how brave you are. And then calculate intake. That ain't no good on a 109. Even though we think it'll run best there, it won't fit in without knocking the compression down. At 115 it has to be. Anybody confused about that? Now, the generation forms seem to be pretty simple, but if you find anything that's confusing about my software, please let me know in the comments. Now we have one more try to confuse you. The graph form. Right now you're looking at the intake and exhaust cam lift profiles. This is the flow figures. It's the flow curve of the head that we're using. And this is the analysis of the camshafts with everything you'd ever want to know. Now we have cam velocity, cam acceleration, and net valve lift. Cam lift, cam velocity, cam acceleration, net valve lift. Now we'll turn off the exhaust profile. We don't really need that anymore. You're going to look at the port velocity. That pink line there is right on top of the maximum point, which is 72 degrees. Right there, the 7 below it is the crank degrees of lag time from piston. So 72 plus 7 is 79, so we move the line to 79. We should be able to read the velocity of the ports, the max velocity of the ports at that number. There's a CFM demand, the piston CFM demand, and there's our port flow based on that opening lift, and right there, the port flow curve. Now we'll turn off the CFM demand and the port CFM, change it to the intake cross-sectional area velocity, and you can see that's 664. That's a good number at peak horsepower, 7 RPM. Max velocity of the minimum cross-section area is a little higher, and so is throat. It's wandering into choke area. Now we'll put that back on there and raise the RPM 500 RPM past peak horsepower RPM. And then we'll check everything, and you can see we're at air by 40 CFM on the CFM demand. Now we can turn that off and look at the velocity of the port. 706 for the intake average cross-sectional area. 748 for the minimum cross-sectional area, and 736 for the throat velocity. Yeah, you drag racers will continue putting more and more gear in the car till the engine finally lays down. At that point, past peak horsepower, you'll have port velocity numbers that you'll know not to exceed. This is not intended to be a simulation. It's just a relatively accurate tool. If the graph form was confusing, please let me know in the comments. Now we're going to go on to the main form. I have a cure for confusion. and I share it with everybody that buys my software. If you have a question, call me. I want to thank Billy for running the computer, and thank you for watching our video. Please stop by our Induction Logic Facebook page.